Hello everyone, I'm Brendan Conway-Smith, and I work with Robert West at Carleton University. Today I'm going to be talking about metacognitive threshold and how we can understand that better. If you're not familiar with that term, that's okay. It is an empirical phenomena that people are trying to model. However, we'll start with some basics. Not that any of you need any refresher, but what is the ultimate goal of cognitive modeling? Well, eventually we're trying to create a unified cognitive architecture, and this was Newell's dream, that can model most, if not all, human cognitive abilities. But speaking of new domains and new frontiers to model, there's a scarcity of metacognitive models right now. There's a lot of opportunities for research as well. So I'm going to start with some basic definitions, just so you know the terms that we're using. Metacognition, well, it's the monitoring and control of your own cognitive processes. So you can monitor your own attention. You're all aware that you're aware right now. You can direct it anywhere. You can monitor and control your own emotions or your memory. And there's also metacognitive sensitivity. Metacognitive sensitivity. So it's the extent to which someone can be aware of their own cognitive processes. So you are more sensitive to the extent that you can detect your awareness level, your emotions. And it's also related to the metacognitive threshold. So greater metacognitive sensitivity involves lowering the threshold to be able to better perceive your internal states. And this is an empirical phenomenon that we're modeling. And metacognitive training has shown overwhelmingly to be able to improve metacognitive metrics. So you can increase your attention, your emotional control, and you can improve your sensitivity to your own internal cognitive stimuli. And meditation is one process that is shown to be able to improve your ability to perceive your internal states. But so far, there's a poverty of cognitive models related to meditation and metacognitive training. So our paper proposes computational mechanisms for how humans can better perceive their internal cognitive processes. Right. Metacognitive training. So research has shown the effectiveness of metacognitive training. You know, the data's in, it's shown to improve all kinds of metrics. Cognitive behavior therapy, metacognitive therapy teaches people to be better at governing their own thoughts and behavior, governing their own thoughts and emotions. This is why cognitive behavior therapy and metacognitive therapy is one of the most effective tools for therapy. In education, there's a reason why metacognition is being inputted into educational systems around the world right now. They're all scrambling and trying to understand this. And it's one of the best predictors of education and learning. So students can be taught to self-monitor and self-control their own learning. And neuroscience has revealed some of the brain regions correlated with attentional training, show the strengthening of regions associated with emotional control. And meditation has shown to improve attention, emotional control, sensitivity, and all these things. So we're trying to understand metacognitive sensitivity in this sense. So how can training improve our ability to perceive our own mental states? Okay, so the question is, how does training allow us to improve our mental states? So meditation, what is happening in the brain? I mean, it's some natural process involving brain mechanisms. What are those mechanisms? And how can we detect internal cognitive signals? And is there a way for a cognitive architecture, like the Calm model, to model this phenomenon? So there's the Calm model there, also known as the standard model of the mind. And our paper is providing a computational account of metacognitive sensitivity using the common model of cognition. So Calm model, just to sort of refresh your memory, is a leading candidate for how the brain functions computationally. There's a convergence across architectures, and it tries to, it's a meta theory for that convergence, those common components necessary for human-like intelligence. There are 5 components: working memory, perception, action, and the 2 we're using now is declarative memory and procedural memory. And you don't need any refreshers for this, but declarative memory is formatted propositionally and structured within semantic networks. And for our purposes, we're using procedural memory in ACT-R as computationally specified as production rules. Productions transform information, they change the state of the system, they complete the task. We're sort of representing them as these little gear icons, these little conveyor belts that move the system. They resolve a problem, they complete a task. These are production rules, they're implicit knowledge. And so this is how we're going to try to understand metacognitive sensitivity. Neurologically, production rules are associated with the 50 millisecond decision timing in the basal ganglia. And so we're considering the mechanisms for how productions can be sped up. So our central claim is that metacognitive training can increase sensitivity by creating faster productions. And faster production cycles could detect subtler internal stimuli and fleeting signals. Now, I should also just sort of pause and say that not all cognitive architectures use production rules in the same way that ACT-R does, but our type of reasoning can be used for all types of production cycles. So we're talking about how production cycles can detect stimuli by taking more samples in a shorter amount of time. Faster productions can detect more stimuli in a shorter amount of time. So greater sensitivity can result from faster productions detecting stimuli at a faster rate. And so we now have an analogy that is the shutter speed of a camera. A shutter speed at 30 frames a second versus 60 frames a second. We know that 30 frames per second is going to be less clear, is going to be less distinct than our ability to detect stimuli at 60 frames a second. More shutter speed, more samples, greater resolution, greater fidelity to what we're trying to understand. So this is one analogy we're trying to use, how more resolution, greater fidelity to the stimuli can be achieved by taking more samples in a shorter amount of time. Now, improved sensitivity, in this sense, can improve our ability to recognize cognitive biases, recognize emotional states. We can monitor our own attention better, keep it on target. We can reflect our own decision-making processes. We can reflect on meta-reasoning cues, and you can notice when your mind wanders, catch it, direct it where you want. And this is some of the benefits of metacognitive training. And one more example to sort of instantiate this better. Therapeutic processes such as anger management is one example. Some have suggested that anger is a secondary emotion. And there's an underlying emotion that creates it, such as fear and hurt. But if you're not sensitive enough to detect the primary emotion that creates the anger, it can cause maladaptive coping, lashing out, substance abuse, all kinds of escapism. But people who go through anger management training tend to increase their metacognitive sensitivity, and meditators will often recognize that right before some reflexive anger, there's a brief, fleeting sadness or a brief, fleeting emotion of fear, a signal that can be easily missed because it's so subtle. And so a refined perception, a refined sensitivity allows people for more adaptive coping. You don't lash out, you deal with the primary emotion. And so this is some of the benefits of metacognitive sensitivity. So this is our central claim. Greater sensitivity results from faster productions detecting subtler signals, and this can help account for meditators' reports of experiencing an improved perception of internal mental states. So we're going to explain some of the mechanisms here for how we can better perceive our own mental states. So our paper presents 4 mechanisms situated in the column model, and we'll go through them one at a time. You can read more about them in our paper, but mechanism 1 is the ticking clock mechanism. So production rules fire when a fixed time is up. This is analogous to the ticking seconds of a clock. And again, this is estimated to be about 50 milliseconds situated in the basal ganglia. And during an interval, productions are identified that match buffer conditions. And when the time is up, the matching production then fires with the highest utility. And using this framework, production time could be sped up by shortening the clock speed, shortening those intervals. This could possibly occur through top-down feedback related to attention, as has been observed in other psychophysical thresholds. There are other psychophysical thresholds that meditation and metacognitive training has shown to improve your sensitivity to: visual thresholds, auditory thresholds, haptic thresholds, interoceptive thresholds, and we're saying that metacognitive sensitivity can be improved through attention as well. And so there's also the fire when ready model mechanism, that ACT-R is essentially a fire when ready model. If no productions rules match the buffer conditions, ACT-R will wait until the buffer condition changes. For example, in memory retrieval, ACT-R waits for the knowledge chunk to be delivered into working memory, into the buffer, and then fires the matching production. So the time equals memory retrieval time plus 50 milliseconds for the production to fire. And using this mechanism, we can say that productions can be made faster using productions that don't wait for information from memory or perception. They match to the stimuli and they fire. And these types of productions can be generated through the production compilation mechanism in ACT-R, and we have another paper on how metacognitive skills can develop through this compilation mechanism in CogSci this year. Mechanism 3 is the narrow focus mechanism. Now, ACT-R is capable of multitasking and even, in a sense, mind wandering if the appropriate productions are available. And we can create faster production rates for a specific type of production by maintaining the buffer conditions such that only a certain type of production can fire. That means that with less distraction, less alternate productions, you have more productions fire in a shorter amount of time, and this is a narrow focus of attention in that sense. Mechanism 4, simpler, faster productions. This is sort of where we hang our hat. In that some productions may be faster than others. Productions range in their complexity of internal actions. The consequences of this is that at the neural level, this could imply more complex productions take longer than simpler productions. You have more gross, more broad, more complex, slower productions that take less samples per minute, and you have faster, subtler, simpler productions with less internal components that take more samples per second. And this allows for a faster detection rate. There's some work by Stewart, Chu, and Eliasmith, and their neural model of the basal ganglia estimates that this would produce a range between approximately 59 to 73 milliseconds for complex productions and 34 to 44 milliseconds for simple productions. And in this case, we can use simpler productions to speed up firing time. So this is our sense of how more complex, slower productions take a certain sample rate of stimuli, but faster, more simpler productions can increase resolution, can increase fidelity of whatever stimuli you're trying to perceive by taking more samples per second. And this isn't in our paper, but we can speculate that a lot of this has to do with what's happening in the basal ganglia during metacognitive training or meditation. Since the basal ganglia sends inhibitory signals, meditation may relax the basal ganglia so that less inhibitory signals are sent. And this allows for faster productions that can perceive subtler internal signals. This may be a little counterintuitive, but it's plausible in that instead of taking more energy, improved attention may actually take less energy as the cost of inhibition is reduced. And so the basal ganglia has shown to regulate a threshold mechanism that has been implicated in what meditators call the restfully alert state. You're alert, your mind is clear, your attention, you're focused, but you're not increasing energy, you're actually reducing the inhibitory signals of the basal ganglia. And so I'll sort of end by giving you a few takeaways. These mechanisms are not mutually exclusive. Meditation or metacognitive training could include one of them or all of them. They all increase sensitivity by speeding up productions, increasing fidelity. This doesn't require, and this is important, it doesn't really require there's a threshold in fact, only that it seems to be that way. It seems that the resulting effect appears that there's a threshold or a sensitivity level that we can increase through faster productions. And so from an architectural standpoint, the particular issue is not regarding thresholds, but rather the complexity and the timing of production rules. And so overall, we say that increasing the rate of production firing can potentially account for reports of increased metacognitive sensitivity as a result of metacognitive training, and the calm model type architecture can model this. Thank you very much. I'll be happy to take any questions.